It's great to be back at IPAM. I used to visit a lot more often when I was on the board, and we've got a member of IPAM management here. And I found a picture of Professor Osher in the 70s, and he still has the same glasses.
I am much better looking than that.
But he's kept the glasses over the years, and they've gone in and out of style, but now they're back in style. So I've got three things to talk about, but I can adapt this talk to the time allowed. So I may or may not get to the last part, but I definitely want to tell you about the first two parts. And basically it's the issue of trying to equip optimization methods with some complexity theory. And that classically has been done in certain domains, but not in others, particularly in non-convex optimization. So I'll talk a little bit about our efforts in those areas. And several of you have heard me talk about this before since 2017. So I'm going to skip over the old stuff and get to some stuff that we've done more recently. And then I want to talk specifically about this. I haven't talked about this stuff before. This phenomenon that a lot of the non-convex problems that show up in learning are actually quite easy to solve. And the explanations for why that's true actually are quite interesting and varied between different problem classes. So I wanted to talk about two pieces of work we've done in that area where the problems have that characteristic. And if there is time at the end, I'll talk a little bit about complexity theory for non-convex optimization in a couple of constrained optimization classes, namely bound constrained optimization and equality constrained. So this is joint with a bunch of my colleagues and team members at Wisconsin and two collaborators from Lehigh. So a little bit of motivation. So there's been a lot of work classically over the years in algorithms for non-convex optimization. In Unconstrained, there's the Newton method. There are quasi-Newton methods, nonlinear variance of conjugate gradient. In constrained optimization, interior point or barrier methods, SQP. These are all very well-known, very established methods, many of them dating back to the 50s. In the case of barrier methods, the SQP, I guess, the 60s, around middle of the 1960s. But if you look in some of the standard textbooks in this area, like my textbook with Nossadal, for example, you see two sorts of results. You see, first of all, you've got these algorithms that generate sequences of points, and the result, one class of results is called global convergence, in quotes. And by that, we usually mean that accumulation points of these sequences satisfy first-order conditions for optimality. And the second kind of result is a rate of convergence result, again in quotes, because that's now understood somewhat differently. But the typical nature of those results are if the sequence is converging to a second-order point with second-order sufficient properties, it converges rapidly, like superlinearly or linearly or even quadratically. So, in the typical optimization literature, there wasn't much work on this issue of global complexity. That is, can you give me an upper bound on how many iterations you'll take to find a first-order point or a second-order point, or maybe an upper bound on the computational cost? There was very little on that, except in certain domains. But recently, there's been a lot more work on that. So first of all, what is a little bit of the context for complexity results? In interior point methods, of course, this was a theme. All the work that was done in the 80s and 90s on interior point for convex problems like LP, QP, conic problems, and so on. In fact, any problems that admit so-called self-concordant barriers. So complexity was a driving force in the development of that class of algorithms. There are also these momentum methods for smooth, unconstrained optimization, going back to Nestrov's work in the heavy ball work, which is in the 80s and maybe even earlier. A lot of that initial development took place in the Russian literature, but then it was rediscovered after about 2010. And now it's very heavily used and researched in recent years, the accelerated gradient. And then there were classically results, again, a lot of it in the Russian literature, but not exclusively, on convergence rates for subgradient and stochastic subgradient methods. But interest in complexity for non-convex optimization is much more recent. And why is that? Well, one is that, first of all, it fills out a big gap in the theory. There were not many results about this for the non-convex case. Secondly, machine learning people got very interested in this, and there was a recognition that started dawning, I don't know, about 10 years ago, that a lot of applications in machine learning really were non-convex. And not only that, but they had these nice properties, and I'll mention this in the middle part of the talk, such that, there were properties like all the saddle points in the problem, that is the points where the gradient was zero, but the Hessian was not positive definite, were strict. That is, if they had a negative eigenvalue, it was like obviously negative. Or there might be problems, and we'll see some of these later, where all the local minima are global. And the third reason is kind of cultural. Machine learning has a strong flavor of theoretical computer science, and so they brought all that baggage with them, and so they decided, okay, we love complexity. So that you can't discount cultural effects here. Okay, so what has been happening in the non-convex case? So a lot of this dates from 2006, and there was a famous paper by Nesterov and Polyak in 2006 where they kind of enhanced the Newton method and proved a global complexity guarantee. A lot of other results here that I won't go into details about, and I sort of grouped these together because these are mostly optimization people up here. But then in the machine learning community, there was a whole lot of work, a little bit more recent, doesn't go back all that far, about proving results about these non-convex problems. So there are people that sort of accelerate. They take the Nesterov method and adapt it in various ways, convexify locally, and then apply a convex accelerated gradient method. There are things where they sort of tweak the Nesterov-Polyak idea or tweak the trust region idea. And then there was this observation that this was a paper of Ben and his collaborators at Berkeley, 3 or 4 years ago, where they observed that if you just apply dumb steepest descent, where you're always moving the negative gradient direction, you have to be incredibly unlucky to get stuck at a saddle point. And it almost never happens. And so there are some methods where people make damn sure that you don't get stuck at a saddle point by injecting noise occasionally. So they'll take a step and then they'll sort of inject some noise and move a little bat away from the current point. And that makes it, even less likely that you'll get stuck at a stationary point that's not a minimizer, at least not a local minimizer. So this is not exhaustive. There's a lot of others, a lot of other work besides that. So, okay, so I'm going to talk in the first part of the talk about just a very general class of smooth non-convex functions, and what we'd like to be able to find is a second order point that satisfies these conditions. That is, the gradient zero, the Hessian is positive semi-definite. I'm going to assume that the function's globally bounded below, so we're not running off to minus infinity, because that's usually pretty easy to detect when that's happening. And I'm going to assume a lot of smoothness here. So the gradient has Lipschitz constant Lg, and the Hessian has another Lipschitz constant Lh. And right away you can write down these very useful bounds, upper bounds. This is a quadratic, this is a cubic, on f of x plus p in terms of f of x, grad f of x, maybe Hessian of f at x, and then these terms here, which are very simple terms, but they involve these Lipschitz constants. So these are kind of essential inequalities to use in analyzing these methods. So we're not going to be able to find a point that exactly satisfies the second order conditions, but we can hope to find one that approximately satisfies these conditions. So if you give me tolerances epsilon g and epsilon h, the goal is I want to give you back a point where the norm of the gradient is less than epsilon g, and the eigenvalues of the Hessian are bigger than minus epsilon h. So these are typically small and positive. And we're going to be looking at iteration complexities, that is, how many iterations of the algorithm do I need, and also operation complexity. So this is, can you actually give me a bound on the computational costs that I need? In order to convert this into this, you need some concept of what is a fundamental operation. And we don't go all the way down to, flops, but what we do identify is a basic operation like evaluation of the gradient of the function, which turns out to be a reasonable thing to use, because it costs about the same as a Hessian vector product. This is the other basic operation in the methods that we've worked on, is the ability to not to know the Hessian itself exactly, but to be able to form a Hessian times vector product for any vector d. Okay, so you need to have a subroutine or a procedure where I give you d, and it gives me back the Hessian times d, without necessarily having explicit representation of the Hessian. So obviously you can do that using finite differencing, approximately, But you can also do it using computational differentiation, and the cost of doing it that way is a small multiple of the cost of evaluating the gradient. So what we used to call computational differentiation or automatic differentiation is called backprop by the people that do neural nets, but it's really sort of the same thing. Okay, so you've heard me many of you have heard me talk about this before, but it's actually very easy to get an extremely basic method where you can prove some sort of complexity guarantee. And what we're interested in here is a number of iterations needed to get a point satisfying those approximate second order conditions in terms of the tolerances, right? So it turns out that you need order of epsilon g to the minus 2, where epsilon g is this tolerance, and epsilon h to the minus 3 iterations. And the algorithm is extremely simple. It basically says, if the gradient is bigger than the threshold that we need, let's just take a steepest descent step with a step length of 1 over Lg, which is the Lipschitz constant for the gradient. And you can show just by using that first bound, that quadratic bound, trivially in one line, you can show that the amount of function decrease you get from that step is at least this much, okay? And the other thing is if the gradient is below this bound, then let's look at the eigenvalues of the Hessian. If the smallest one is above minus epsilon h, you're done. You've found an approximate second order point. If it's less than minus epsilon h, let's take a step in this direction dk, that is the direction that achieves the most negative eigenvalue, and take a step of that length. And again, by using the cubic upper bound, you can show that you achieve that much decrease in the function related to epsilon h cubed.
Steve, real quick. So the first one you can satisfy up to a constant, the first inequality up to a constant using line search, right?
Yeah.
But then, is it similarly?
Similarly, the second one, you could do backtracking if you didn't.
You don't actually have to know LH.
No.
Do that by backtracking.
No, you can do it and that's what we do in the actual algorithms. Yeah, where we don't necessarily know these constants. Okay, so in order to turn this into a complexity, look, you just say, okay, I start at x naught, so function value there is f of x naught. I've got this lower bound f low, so there's a gap, optimality, or an upper bound on the optimality gap between those two values. I'm making this much progress, at least at each iteration, the min of those two things. So in order to turn that into a bound on the number of iterations, I just divide the gap by those quantities that I just showed you. And that's where you get the epsilon g minus 2, epsilon h minus 3 coming in. So, so this very sort of brain-dead algorithm already has some sort of complexity bound. And actually, the optimal bounds are not too much better than this. You can turn this epsilon g to the minus 2 into an epsilon g minus 3 over 2, but that's a lot of work. And we do that, and those papers that I cited earlier from 2017 also achieve the same sorts of bounds. So, okay, so how expensive is each iteration? Well, if you take a step of the first kind, you're just evaluating a gradient. That's not very expensive. If you're taking this step here, you need to know the smallest eigenvalue. And the most obvious way to do that is do a complete eigenvalue factorization. That's an order n cubed process in general. Okay, well, you might say, well, you don't really need that because all you need is the smallest one. And you don't even need the smallest one. You just need one that's smaller than minus epsilon h. And it turns out you can get those a lot more cheaply. Okay, so in the operation complexity, in fact, if we use a Lanchos type procedure to get a decent approximation to minus epsilon h, the approximate cost of that is order of epsilon h to the minus 1/2. And so you multiply the iteration count by the cost of this operation, which is the expensive one, you end up with the operation count being that factor worse than the iteration count, which I didn't write down. But basically, the epsilon h to the minus 3 becomes epsilon h to the minus 7 over 2 when you're talking about operations. Okay, so that's kind of the benchmark, the obvious dumb algorithm. So we had two papers on line search methods that sort of build on that. The main differences are they use Newton type steps. So we don't just take negative curvature steps and negative gradient steps. We compute an approximation to the Newton step using conjugate gradient. And the trick is that we don't want to spend too much time in the conjugate gradient procedure. This is classical conjugate gradient, which is for positive, symmetric, positive, definite linear systems. A couple of things can go wrong. One is that the Hessian need not be positive definite. We damp it a little bit for reasons that I'll explain in a moment. But the other thing is we know that conjugate gradient runs for a total of, at most, a total of n iterations. But that's going to kill our complexity if we run for all n iterations. So we have to sort of engineer things that we take no more than this many iterations. And so that takes a little bit of messing around. I'm not going to go into the details of this. The second thing is that, as I mentioned a moment ago, occasionally we need to explicitly calculate a negative curvature direction. The Newton step is not the whole story here. If we detect that the Hessian has significant negative curvature, then we go searching for an approximation to the most negative curvature direction. And as I mentioned before, what we end up with is we manage to shave a factor of epsilon h to the minus 1/2 off the, epsilon g to the minus 1/2 off one of the complexities. And if we set epsilon g to be the square root of epsilon h, we get an overall complexity, overall operation complexity of epsilon g to minus 7/4. And that takes into account the cost of running conjugate gradient here and the cost of running this randomized Lanchos. Okay, so that was the old stuff. So now, more recently, we've done a truss region version of this, motivated by the fact that one of the most popular practical methods that people use for large-scale constrained, unconstrained optimization is the so-called Steihaug method, which I'll describe on the next slide. But it uses a so-called truss region framework, which again is a pretty classical idea in optimization. The idea of truss region is that you form a quadratic model, and very often you use the Taylor series quadratic approximation, and then you decide, okay, I trust that approximation within some ball or box or something. So for example, I might trust this to be a pretty good approximation of f as long as s has a radius less than delta k. And so you solve a problem of minimizing over that ball, you minimize this quadratic, and you get sk from that, and then you see if that's a good step. So you evaluate f at the new point, you check out how much improvement did you get in f from xk to xk plus sk. You compare that with the amount of improvement that was predicted by this model. If that thing's, sort of close to 1, or at least not negative, you decide, okay, this is a reasonable step, so let's take it. If it's really close to 1, you decide, well, I was being a little conservative with the size of the ball here. So if this ratio is very close to 1, this is a very close approximation to f. So let's increase the size of the ball for the next iteration. Otherwise, if this is very small, like less than 10 to the minus 3, then this wasn't a very good approximation. So let's shrink the delta and reject the step and try computing it again. Okay, so a very classical idea. Steihaug's variant on this, very clever idea, was that he said, okay, if you've got a very large-scale problem, it's sort of expensive to solve this problem. If you know all the eigenvalues of f, you can do it in closed form, or almost in closed form. But otherwise, this is kind of expensive. So his idea was, let's run conjugate gradient to minimize this. Okay, it's a quadratic, may or may not be convex. Let's just hope that it's convex and run CG. So then what happens is that if CG detects non-convexity, that if it detects negative eigenvalues in the Hessian, he just moves along that negative curvature direction until he hits the boundary of the truss region ball and uses that as the step. If one of the conjugate gradient iterates crosses the boundary of the truss region, he stops at the truss region boundary and uses that as the step. And so this has turned out to be a practical method because you never need to know the Hessian explicitly. You just need to be able to do Hessian vector multipliers, which is what you need to do in order to run conjugate gradient. So it's popular, it's a practical approach. If your initial guess is 0, you can show that the very first step of conjugate gradient takes you to what's called the Cauchy point. That is the minimizing value of the quadratic model along the negative gradient direction of f. And that's all you need to guarantee this, that limit points are first order. The other thing about classical truss region, one of the reasons it's popular, and it's become popular again, is that it can handle indefiniteness in the Hessian in a natural way. So that this problem still has a solution even if this matrix is indefinite. Now that's only handled in a very crude way in Steihaug's method, because if he happens to stumble across indefiniteness, He just has this thing of moving to the boundary. But you can prove convergence of this. You can't prove any rate guarantees. There's no complexity guarantees on this. So we wanted to sort of mess with this algorithm enough to be able to equip it with complexity guarantees using some of the same ideas we used in the line search method. It turns out it wasn't completely trivial. It wasn't just an obvious extension from the line search idea, but it does look a lot like it. Again, it takes two kinds of steps. It takes this sort of slightly damp Newton type step and tries minimizing that over the ball, again using conjugate gradient, but now it has to sort of take precautions to make sure that you don't spend too long in conjugate gradient, so long that you'll destroy the complexity. And it still occasionally needs to compute, actually go searching for the minimum eigenvalue of the Hessian. So it still has sort of two of the same basic ingredients that we use in the line search approach. The thing about this damping, by the way, I should say a little bit about that. Those of you who've run conjugate gradient on a matrix that's symmetric but not positive definite know that conjugate gradient has this almost magical property of homing in on the negative eigenvalue, right? If there is a negative eigenvalue, conjugate gradient pretty much will always find it. Proving that that's true, in fact, you can sort of prove things about that, but proving it and proving how fast that happens is not trivial. There are these papers from about 20 years ago by these two authors where they actually get bounds on Lanczos type methods, of which conjugate gradient sort of is one, where they sort of get an estimate of how long it takes to get to the extreme eigenvalues. But in practice, it happens very quickly. And so this minimum eigenvalue oracle is almost never needed, because almost always if we try to do CG on this, it will find the negative eigenvalue. The idea of this is we need it for the complexity. We need to boost the most negative eigenvalue by 2 times epsilon h so that we don't spend so much time in the CG for technical reasons that I can't really go into much more detail on. But in practice, it makes almost no difference because this thing is small anyway. So it just applies a very small shift to the Hessian. Yeah, this is the minimum eigenvalue oracle. I guess the only thing I need to point out here is that you can implement it using Lanczos, and there is a probability of failure. You do get failure if your randomized starting vector happens to be in a really bad subspace. If it doesn't have any component in the space of negative eigenvalues, this will fail. But of course, that pretty much never happens if you take a randomized starting point. But you will see this log delta show up in the complexity estimates because we have to allow for the probability that you get really unlucky. Okay, so what we end up with, just sort of cutting to the chase, is we basically get the same sort of complexity results as we get for the line search case. If we set the epsilon h to be the square root of the epsilon g, we get the same bound on the number of iterations and the same bound on the number of matrix vector products or gradient evaluations. So that's basically the story there. We went and implemented this. We looked at this QTIS test set, which is a battery of test problems in nonlinear optimization. We just picked the ones that weren't necessarily convex. We tried a bunch of variants of this method. It turned out that and these are so-called performance profiles. This is my colleague George Moret at Argonne back in the 90s, came up with this way of kind of graphically capturing battery test problems. So basically, I guess all I need to really tell you is that the high lines are the ones that are performing best, the ones that are highest on this chart. The asymptotes out here is how many you end up, what fraction you end up solving. So in this case, it's 38 out of 41, which is what, 0.92 or something, 92%. That's another truss region method. That's something that Robinson and Frank Curtis invented. But it's not, it needs a lot more work than this one. It has complexity guarantees, but they're not as good. But the bottom line here is that the red line is the best one. And this was basically the original Steihaug method. So we did pay a little bit of a price for the kind of extra bells and whistles that we put in to equip it with a complexity theory, but really not very much, because these other lines here are, very close.
Is the performance profile time or iteration?
Yeah, I think it's time. Which is the fair one, right?
Yeah.
So, but the iteration counts are not all that different. Okay, so this is the second part of the talk. I wanted to tell you about.
Just real quick, sorry.
Yeah.
Just to go back to that last, the conclusion of that first part. So the conclusion that, so you have these epsilon guarantees,
Right.
complexity guarantees, and it performs worse than the heuristic that people did before.
Yeah, so they perform worse, but not much worse. So it turns out, you know, ideally you'd like to see it actually do a little bit better, but it turns out the extra checks you have to put in to guarantee the complexity slightly degrade the performance, but very little. And these other algorithms that people have proposed, like the Ducci one and the Allard-Hazan, they're not at all practical methods. These are like, you know, crazy methods that you'd never want to implement. So what we tried to do is to start with practical methods, tweak them a little bit to make them achieve the same complexity bounds, and kind of show that they were still practical at the end of that.
I guess the question I'm left with, and we could
Yeah.
but why do we care about the complexity bounds? If they're degrading performance, like what are they bringing to the table?
Well, they bring to the table the fact that you can now prove these extra theoretical things about the algorithm, so machine learning people will take them seriously. Yeah, that's all I can say. I mean, it is a richer theory than what you had in the old days when you just had accumulation points of stationary and you know.
You're guaranteeing that you're getting to a state.
Right. There's a global bound on the number of iterations now that you didn't have before.
What's this spelled?
Steinhaug, yeah.
Steinhaug, that also.
That has no complexity guarantee.
But doesn't even have convergence guarantee.
Yeah, he has a first order convergence guarantee. We have a second order, yeah.
But you have a second order.
Yeah, that's the difference. Okay, so this is something something that you're, I think, pretty much all of you will be familiar with. That there's tons of non-convexity now in modern machine learning, starting with neural nets, but also phase retrieval problems and low-rank matrix problems. But this non-convexity is often benign. So it's been noted from very early on, including the Bureau-Montero paper, I think, that if you just run a fairly garden variety nonlinear optimization method, it will typically find the global minimum, or at least a useful solution. It won't get stuck at a local minimum. And there is some theory to explain this phenomenon in certain cases. And there's a very nice review paper by these authors that focuses on low-rank matrix problems from a couple of years ago. And and Ben and many other people here have done work on this. The statistical properties, if you make certain assumptions on the statistical properties of the data that sets up the problem, you can prove things like that all the local minima are global. So as long as you have an algorithm like the ones I've been talking about that find local minima, then you know you've basically solved the problem, because those minima are global. Another one is that often you can show that saddle points are strict saddles. That is, if you have a stationary point that's not a minimum, it's got negative curvature in the Hessian, so it's easy to escape from by using these techniques like the minimum eigenvalue oracle that I talked about. And another stream of work, which I think is less important these days, but certainly there were quite a few papers on this a few years ago, was that they had sort of clever techniques for finding initial points that were guaranteed to put you close to a global minimum. So if you subsequently, starting from that point, ran just a steepest descent algorithm, you're guaranteed to go to the global minimum. So in these senses, these were not sort of typical general non-convex optimization problems like the one I've talked about so far. So here's an example, matrix completion, and I sort of think it's great that the three inventors of matrix completion are sitting in a very tight cluster over here. Yeah, so they wrote the original paper back in 2008, I guess. I guess you invented it at IMA, right? Not IPAM. So IMA gets the credit. Yeah, anyway. Not like compressed sensing, that was invented at IPAM. Yeah. All right, okay, so the story here is that you've got the unknown is a matrix X, and you're making these linear observations of X. So you're taking these observations which are sort of linear combinations of elements of X. I'm going to assume here that X is symmetric, although it doesn't have to be. Classically, it can be non-symmetric as well. So you can express these linear observations as a matrix inner product of some matrix AJ and the X. So the way that you guys did it back in the day was you had this nuclear norm penalty, right? That's what you had in the original paper. And so they showed that analogously to what's happened in compressed sensing, where you have a L2 norm and an L1 norm, they took a Frobenius norm and combined it with a nuclear norm, which is a sum of singular values, or in this case, a sum of eigenvalues, and showed that, for appropriate choice of regularization parameter, you could recover a low-rank solution. But another way to do this thing is you explicitly parameterize the matrix by two skinny factors, express it as a product of, in this case, a skinny matrix with itself because it's symmetric. And the drawback of that is it gives you a non-convex problem. It's no longer convex in the Z, okay, or the factors, however you choose to factorize it. But it turns out that under certain assumptions, it's one of these benign non-convex problems. So if you make some assumptions like the following, one is that the AJs have to satisfy sort of a restricted isometry property. That is, if you look at the sum of all the samples of AJ on X, that it's almost orthogonal. It's between it's close to a factor of 1 times the Frobenius norm of X. This has to be true only for all X with rank at most Q. So it only has to be true for low rank X's. And then this delta Q has to be small. So if you've got this property holding, it sort of means that you're adequately sampling across the whole matrix. Then you can write this formulation. If you just plug in X equals ZZ transpose, you get this least squares formulation, which, as I said, is non-convex. But if you've got those properties that I had on the previous slide holding, you can show that all the minima are global and that all the stationary points of F that are not strict have negative curvature. What does that mean? So I guess all the stationary points that are not solutions maybe have negative curvature or something like that. This was this paper by Nati in 2016. I think that's where it was proved. What's that? Yeah, I think it should be not solutions. That are not solutions have negative curvature. So
But they have strict negative curvatures.
they have strict negative curvature, so you can't escape from them. Yeah, right. So this is this surprise. So as long as you've got an algorithm that can find, a second order point, then it's going to find a global solution. That's basically what this is saying. Okay, and then there were some papers. I think John Lafferty had a paper like this, where he showed that you can actually initialize this problem in a clever way by taking a certain sort of clever combination of the sensing matrices AJ, and you could show that that puts you close to a solution. I forget how you choose the Y's. Oh, the Y's are the observations. Yeah, so you can kind of show, because of this almost orthogonality properties of the AJ, you can sort of reason that that matrix, the Yj times AJ summed over J, actually is pretty close to being a solution. And so they can rigorously show that, and they can sort of get a bound on how many iterations you need. But I just wanted this very simple case to illustrate what happens. Even though this is a non-convex problem, you do have these nice properties. So, okay, so we looked at a class just very recently. This is still being written up. We looked at a class that was analyzed in this paper by Mike Wakin and Gongguo Tang and Jiwei Zhu, and I think one or two other authors, where they looked at sort of generically at a class of low-rank matrix optimization problems. They're not necessarily symmetric. So UV transpose is the low-rank representation of the argument. They sort of structure the UV, they mash them together into a matrix W like this, and sometimes they talk about F of W, which is defined as the real objective of the UV transpose. And this could be something like that sum of squares objective of the observations. Now, you can sort of tell right away that there's an ambiguity in the solution here. If I multiply U by 2 and divide V by 2, I get the same UV transpose. And so they try to eliminate that by adding on this regularization term, which basically eliminates that kind of scaling ambiguity. But it doesn't affect the solution, because you can show that this is 0 at a reasonable solution. So this is the function that they sort of work with. And their paper is actually really kind of complicated. By the way, they make an assumption a lot like that one that I had in the matrix completion case, namely that the action of the Hessian on two low-rank matrices T, where these are ranked less than 4R, is bounded between two multiples of the Frobenius norm of T squared. So this is something like that, near orthonormality assumption that I mentioned earlier. But they also need the A and B constant to satisfy this sort of relationship. The X star is the solution of the problem. It's the actual minimizer of little f. It's the one where the gradient 0. And we're assuming that it has rank exactly R, and that the lowest singular value, the smallest non-zero singular value, sigma R, satisfies this relationship to B and A. So a lot of assumptions here, really technical. This paper is kind of hard to pull apart. But basically what they show is that you can take the space that W lives in, W is just the alternative representation of U and V, you can take that space and bust it up into 3 regions. And basically there's a region where you're close to this minimizer, closer in distance than the sigma r to the 1/2. There's another region, possibly overlapping, this isn't necessarily a partition, but it does cover the whole space. There's another region where you've got significant negative curvature in the Hessian of the G, which is the thing that you're minimizing. And there's a third region where the gradient is large in terms of, again, in terms of sigma r and the norm of W. So this is kind of nice from an optimization point of view, because we know that if we're in this region, we could potentially take one of those negative curvature steps and make decent progress in the function. If you're in this region, you can take just a negative gradient step, just like I did in the stupid method right at the start. And if you're in this region, it turns out, if you're close to the solution, it turns out that you can take negative gradient steps and you can prove that they converge at a linear rate. Now, all of this is great news from the point of view of complexity, because there's no epsilons anywhere in here. All of these regions are defined in terms of the minimum non-zero eigenvalue of the x star. And so what this means is that we can get complexity rates that no longer have those epsilon g to the minus 3/2 and epsilon h to the minus 3 in them. They're going to have the sigma r in them, but they're going to be almost independent of the precision that we need. The epsilon's only going to enter in as a log. So that's sort of a dramatic improvement. So here's a sketch of the method. Now, obviously, if we knew the sigma r, you could just take one of those algorithms that I talked about in the first part of the talk and tweak it a little bit. Instead of testing against the epsilons, you could put something involving sigma r in there and get a better convergence. But that's cheating because, of course, you're not going to know this thing. So we have to design a method where we keep track of this. We introduce this parameter gamma k, which is our sort of latest estimate of sigma r. And we try to estimate those regions R1, R2, R3 in terms of the gamma k. And if it turns out it looks like we've got that wrong, then we just halve the gamma k and try again. So we try to adapt, we try to sort of figure out adaptively what that sigma r is. So this is a sketch of the method. The paper is extremely technical, but the basic idea is simple, and it's almost like the stupid algorithm at the start. First of all, you just test to see if the gradient is large. If it is, you take a steepest descent step, just like I did before. Otherwise, if you're below threshold on the gradient, you test for negative curvature. If you've got negative curvature, significant negative curvature, you do a backtracking line search along that direction. Okay? But if it turns out the gradient is small and there isn't much negative curvature, we might be in that R1 region, the region that we're close to x star. And then we start taking negative gradient steps, and we keep checking to see if we're converging linearly. And it turns out you can check for that. There's a test that will work. And if we are converging linearly, great. We're going to home in on the solution quite quickly. If we're not, then it turns out we must have screwed up by thinking we're in region 1. So let's halve the gamma k and then go back into the outer loop. So that's the basic idea. So it tries to sort of figure out adaptively what the 3 regions are and act accordingly. So the bottom line is that we can show that the dependence on the tolerance that we want to converge to only enters through a log, and that is in that final linear phase when we're taking steepest descent steps to x star. We've homed into the neighborhood of the solution. Because it's converging linearly, we get a log epsilon dependence in that loop. In the other 2 parts of the loop, where we're taking the negative gradient step or the negative curvature step, there's no epsilon there. We've got a dependence instead on the sigma r to the minus 3. So by sort of knowing, by dealing with this specific class of problems, low-rank matrix problems, under the assumptions that I've made, we're able to sort of dramatically improve the complexity results. So it's another instance of being able to prove that you've got this this nice benign non-convexity structure. So that was one of our examples of benign non-convexity. Here's the second one, and this very much relates to Daniel Kuhn's talk yesterday. So this is a topic that was very hot, maybe a year or 2 ago. I don't know how hot it is anymore, adversarial machine learning. I think it might be slightly past that little peak of hype. but it's still of great interest when you're talking about applications like self-driving cars. But this is one picture that's used to illustrate it. If you train a deep net on a set of images, it turns out that you can attack it, if you're very clever, you can attack it in very subtle ways that will really mess it up. So if you take this image of a pig and add on some noise, it's not random noise, it's very carefully chosen noise. And this is, the scale of the noise here is in a much bigger, a different scale from this. But if you add that to that, you get something that's pretty much indistinguishable from this. But it turns out that the neural net will classify that as a wombat. And a wombat is an Australian marsupial, for those of you that don't know. Okay, and so this is a problem, right? Because it means that if you are very clever, you can confuse the heck out of classification engines. And so the first reaction that people had to try to overcome this was to do this adversarial classification. So during the training, you would try to choose a boundary so that it didn't just separate the red points from the blue points, but it sort of drew a ball around each one of size epsilon and said, let's try to separate the ball. Let's try to choose a hyperplane that not only separates the points like this one does, but separates the balls. So in this case, you'd sort of prefer this hyperplane because it clearly separates a ball around the points as well. So basically, you sort of want to push the separation bound or the decision boundary away from the points as much as you can. So the problem is perceived as being the decision boundary is too close to the data, and we want to push it away as much as we can. So, okay, so let's take a very simple problem of adversarial binary classification. So here I've got a bunch of points x. I've labeled them with y equals plus or minus 1, according to which of the two classes that they're in. And ultimately I want to find a mapping f that has the same sign as y. Okay, so that if f of x is positive, that corresponds to the points with label plus 1 and vice versa. So in other words, if the product of y with f of x is negative, it means we've misclassified the point. It's on the wrong side of the boundary. And so what we'd like to do is to choose a function f from whatever class that we're using so that the probability of misclassifying over the true distribution that the training set's being drawn from is as small as possible. Okay? So, so first of all, we define a distance to the classification boundary. And this basically is the smallest perturbation you can apply to x to carry it over to the wrong side of the decision boundary. So if x is already misclassified, obviously this distance is 0. But if it's correctly classified, delta is how much of a perturbation you have to make to take it onto the boundary, right on the verge of crossing over. And you can consider, okay, so given that definition, let's think about three things that you could try to optimize in choosing the f. So one is that you can try to minimize the perturbation robustness. In other words, you can say, over the distribution that these points are being drawn from, I want to make sure that the probability of being within epsilon of the boundary, not just being on the wrong side of the boundary, but being within epsilon, is as small as possible, okay? So that you're allowing this margin epsilon, you want to say, I want to stay more than epsilon away from the boundary if possible. So that's one thing you can consider. The second one is to just try to minimize the expected, maximize the expected distance to the boundary over all the distribution of x and y. That turns out probably not to be so interesting. And the third one is to do this distributionally robust idea, which is what Daniel talked about yesterday, which is to say P might not be the correct distribution. So let's draw a ball around P, a ball in distribution space, and let's solve this max problem. So given an F, let me look for the Q, the distribution Q within epsilon of the distribution P that makes this thing as bad as possible, makes the probability of being on the wrong side of the boundary as bad as possible. And we'd like to choose the F to minimize that, okay? To minimize against the uncertainty in the distribution. Okay, so we don't know, so of course we don't know the underlying distribution. All we've got is a training set, and you can think of that as being an empirical sample from the underlying distribution. Let's call that p hat n. So that's what Daniel had as a series of spikes, right? Which is in distribution space, it's a series of spikes corresponding to the observations that you make. And so what we want to do is to search in the ball around, or the Wasserstein ball. We use an L1 Wasserstein measure around that empirical distribution p hat n, and we want to choose the F that minimizes this max, and the max is the worst distribution in that ball. Now the difference between what we do here and what Daniel had a hinge loss in here, and he found that in closed form he could get a sort of regularized hinge loss, as I recall. Here we've got sort of a 0-1 loss. We incur kind of a loss of 1 if we're on the wrong side of the boundary and 0 if we're on the right side. So it's a discontinuous objective that we're dealing with here. So when we do this regularization, we don't get a nice smooth objective anymore, as we'll see in a moment. Okay, so, but we do get a closed form solution, okay? And we were referring to these papers, that some of which were referred to in Daniel's talk yesterday. So we use this L1, we use the Wasserstein distance, we actually use an L1 measure in here, and that was described yesterday, so I can't do any better than Daniel's description, so I won't even try. But I've got a picture of what it looks like and how it differs from the idea of just drawing a ball around each point. So if my goal here is to look in the Wasserstein ball of radius epsilon around Pn, so Pn is defined by the locations of these training points, then what is the worst case, given a decision boundary here, which is defined, the F is basically defined by this line, we just got a linear problem, what is the worst case distribution in this ball with respect to this boundary? And it turns out you can compute it in closed form. What you do is you go over these points and you order them in terms of their distance from the boundary. And you say, I'm going to move as many of them to the boundary as I can without exceeding this budget of epsilon times n, where n is the size of the training example and epsilon is the radius of the ball. So basically the ones that are closest that you can move to the boundary, you move them all to the boundary, you stop when you blow the budget. And usually there's a little bit left over, and the way that you deal with that is that you split this point and move some of it towards the boundary, or you move some of it to the boundary and leave some of the mass here. So it's sort of equivalent to moving it part way to the boundary. So in other words, you can get a closed form solution to what is the worst case distribution in that ball. Okay, in this special case of a linear classifier and this discrete distribution. So it looks a little bit different from the adversarial case, and it will give you generally different solutions. Okay, now what happens when you turn that into an optimization problem? Well, we can use some of that machinery that was described in Daniel's talk, but the bottom line is we end up with this regularized ramp function loss. So this looks very much like a hinge loss, except this is not a hinge. Instead of being a hinge, it's this function here, the blue one. The hinge would be the one with the red dotted line. But we've got this non-convex function here with these blue lines. And then we've also got this regularization term, much like came up yesterday. Okay? So we've got to minimize this non-convex function. It's non-convex and it's also non-differentiable. So it looks like it's nasty. And in fact, we tried to do it using special purpose integer programming solvers. So NAM, my postdoc, worked very hard on designing an integer programming solver using outer approximations and all this other stuff. But we really couldn't get it to work with more than about 75 samples. So then we said, well, let's do something naive and use non-convex optimization. So first of all, let's get rid of the non-smoothness in the ramp function by designing a kind of a smooth version of the ramp function, parameterized by some parameter sigma. And the closer sigma is to 0, the closer we approximate it. So even when we get sigma down to 0.1, that's the green line, we're already very close. So, so that at least smooths out the kink. We can deal with this 2 norm here by just observing that epsilon times W2, this actually gives us the same solution as if we replace the W2 with the W2 squared, as long as we change the epsilon a little bit. So we can actually smooth that out as well. That might not even be necessary because the W is not 0 anyway, so you could probably work directly with that one, but anyway, we work with this one. So now we've got a smooth non-convex optimization problem, and we just solve that using our favorite methods, nonlinear conjugate gradient, LB of GS, whatever you like, okay? And what we found, well, first of all, I generated a toy data set that looks like this. I'm very aware of the time, so I promise not to go over. All right, so this was a toy data set. So I just picked some dimension, 10, 20, 50, whatever. I generated a bunch of points in a box, and I said, let's classify according to the sign of x1. Okay, so the classification boundary just lines up with one of the coordinate directions, like that. And so what we're trying to do is to recover, in the distributional robust sense, we're trying to recover that, the obvious classification boundary. So the thing that surprised me a little bit when I ran it was that it always found the answer. If I started with this perfectly classified set, if I initialized the initial W from any point, it always basically went to the right solution. And I thought that was a little surprising because this is very obviously a non-convex problem. And I found even more surprisingly that if I took this set and flipped a bunch of the labels, if I just changed some of these blues to reds and vice versa at random, in fact, even I could go up to like flipping 20% of them, I still basically got the same solution back again. And to some extent, that's good because that LR, that RAM function, is pretty robust to high outliers. So if you've got, the point way over here that's red, it'll pretty much ignore that. It won't contribute that much to the objective. So that's kind of healthy. But it was still surprising to me that it almost always got back to the same solution. Once you got above 20%, it started to occasionally find local solutions. But, 8 times out of 10, it would still find the global one. So I got to thinking, why the heck is that? So I sort of looked a little more closely at this function that we're minimizing, this regularized loss thing, and I realized that if you just write down optimal or stationary conditions for that and rearrange it, you get the W, this should be W star here as well. You just get that W star is equal to this thing here. Now if you look at this, in particular look at the first component of this, then yi times the first component of xi is always positive, by the way I've defined the problem. It's classifying according to the first component. So that means this term always has the same sign for the first component. These guys are always negative. The slope of the ramp, the smooth ramp, is always negative. So basically we've got a summation here where in the first term, everything in this summation is positive. All the terms are positive. In all of the other components, 2 through D, because I'm, and specifying the training data is randomized over a uniform random distribution, these things have 50% of the time, they have positive signs, 50% negative. So essentially what's happening is that the first component is really going to dominate all the others. And that's exactly what we want, because our true decision boundary is 1, 0, 0, 0, 0. So that kind of explains in a very hand-wavy way why we recover the original one. And it's even simpler than the explanation that we get in matrix low-rank matrix optimization, where the reason that we can always find the global min is that whenever you've got a stationary first-order point, the second derivative is telling you how to get away from it. Here we don't even have spurious first-order points. The only stationary points we have is the solution. And so it's an even simpler explanation. That also kind of explains why even when we flip the labels, this is still a solution, because basically when we flip the labels, if we flip 20% of the labels, that means that 80% of these terms will have one sign and 20% will have the other sign. Whereas that's in the first component. Whereas for the second through the dth component, it's still going to be 50-50. So the first component is still going to have a bias in it. And so that 1, 0, 0 is still going to be a solution. So okay, I didn't get to do the third part, which is fine. But this was, so I needed to use the adaptive strategy, the bailout strategy. But let me just go straight to the summary. So my thesis is that complexity analysis of non-convex algorithms, particularly of established practical algorithms, gives us a little bit of extra insight into the behavior, and maybe even suggests some improvements that can sometimes be helpful. That you can explicitly check that you're not stuck at a second order at a point with negative curvature, and if you are, you know how to get away from it. This we all know, non-convex problems are ubiquitous in machine learning, but the performance of models and algorithms is not well explained by the classical theory, so we have to drill a little bit down into the structure, understand what's going on, and I think it's interesting to do that. So thank you.